Is my screen visible, Ashutosh?
Your camera is visible. Yes, your face is visible.
Okay. Okay, let us start. Okay. Okay, good evening, everyone. We hope you are all safe on the other side. We have reached the second and the final leg of the event, Emulate Talk. I'm elated and gratified to welcome the speaker of today's talk, Mr. Vidyuranya Sai. The accolades to his name are manifold and varied. He has worked with companies like Amazon and DE Shaw during his career. He has completed his post-graduation from the Oxford University and currently works in Sensyne Health in the United Kingdom. Today, he will be speaking about the field of computer vision and the current trends in machine learning with some special insight into the projects in which he is currently working on. Please, I'm honored to give you the stage. You may start at any time.
Thank you, Abhijit. Thank you for the nice introduction. Let me just share my screen. Uh, yeah, I hope you can see my screen and my video as well.
Yes, sir.
Sure, sure. Uh, so let's get started. So before we actually do that, I was told that the background of people attending this talk would be varied with respect to machine learning. So I assume there would be folks who have already done some research in computer vision. And on the other hand, there might be people who have just got introduced into this field of machine learning. So I'll try to ensure that I cater to almost all of you. I hope that everyone has something or the other to take away from this talk. So yeah, let's get started. So this is the agenda that we would talk about for today. First, I would be talking about traditional computer vision, and then we'll look at a few applications of modern machine learning in computer vision, like visual question answering. And while I do that, we'll talk a bit about scene graphs and graph neural networks. So two really exciting fields and research directions. And after that, we will be talking a bit more about few-shot learning, which has actually gained a lot of traction in the recent years. Now, we'll also discuss why it has gained so much traction and what's actually happening in the field of few-shot learning and visual question answering. So yeah, so before we actually get into the machine learning part of computer vision, so I think it's always good to know a bit about traditional computer vision for mainly two reasons. Firstly, it's always good to know how the field has evolved over the past few decades. So computer vision is something that was there even before all this hype around machine learning, etc. So I think the first few publications in computer vision date back to 1960s. And the second reason why we would probably want to learn about traditional computer vision techniques is because the startups which are there or even established companies, even today, they do use some traditional computer vision methods in their applications. That's mainly because these are much less expensive compared to the machine learning models wherein you need to have a lot of computational resources. So I'll talk. I won't get into a lot of details about this traditional methods, but I'll just give you one application, which is basically about edge detection, and then maybe I'll give you a few pointers on how you can go ahead if you want to read a bit more about this field. So let's get started with edge detection. So what happens in edge detection is you're given an image, for example, this image on the left, and then the system basically has to output the edges that are present in the image. For example, like if you see on the right side, we have all the edges that are in the image given on the left. If we want to get these edges, like if we have to predict these edges, what should the system do? Now look at it. When is an edge created? It is basically created when there is a sudden change in the intensity value when you're moving in any direction. For example, if I have to detect this vertical edge, small vertical edge on the brick, now that comes up because there is a lot of change in the intensity when I'm moving in the x direction from left to right. So when I'm moving in a direction, and if I sense a drastic change or a sudden change in the intensity value, I can consider that as an edge. So how do we do that? So basically, if you have to get the rate of change of anything, we simply use differentiation. So you see here the formula for differentiation. So I can just say f of x plus h minus f of x by h, limit h tends to 0. But here if you see that our f here is basically the intensity values of the pixels in the image. If you see f, it is not a continuous function. That's because you do not have any value when x is equal to 1.5 or 1.6, because you only have pixel values at x is equal to 1, x is equal to 2, x is equal to 3. Let's say, for example, you have a 256 into 256 image, then you would only have x is equal to 1, 2, 3, 4 until 256. So f is not exactly a continuous function in our scenario. So in this case, the minimum value that h can take is basically 1. So if we do that, this differentiation would basically be a simple subtraction. It would be f of x plus 1 minus f of x. So that would give us the rate of the rate of change of intensity values in x direction. So if I have to represent that in matrix notation, so it would be something like this. It would be f of, so if I take the intensity values and then multiply it with a matrix, so what is this basically doing? It is basically saying f of x plus 1 minus f of x. So this is how we can get the intensity values in the x direction. Simple. Now, if you also want to find the rate of change of the intensity values in the y direction, we also have to do the same sort of differentiation, for which in our case a subtraction in the y direction. Now it would also be the same. So if you have to get it in the y direction, what you have to do is basically take the intensity value of y plus 1 minus f of y plus 1 minus f of y. So if you represent that in matrix notation, it's very similar to the x direction, but you just have to transpose it just for the sake of matrices when you multiply them. So in this fashion, you can get the rate of change of intensities, or you can basically get the derivatives in x and y directions. Now that you have two derivatives in x and y, if you want to get a magnitude, you can simply do a square root of x square plus y square, and that gives you the magnitude of this derivative at every pixel, right? Once we get the magnitude of derivative at every pixel, it is basically suggesting you how strong is an edge over there, like how strong is the change of intensity value at that pixel. That's what this magnitude is going to tell us. Now, can we say that if the rate of change of intensity is greater than 0, I mean, if there is some change in the intensity value, can we consider it as an edge? The answer is no, because, for example, the image might be blurred, or even in this, if you see the brick walls, there might be some dots or spots on the bricks, but you cannot consider them as edges because there is a lot of noise. So what you simply do is you basically threshold the magnitude, and then you say if the magnitude is greater than a specific value, let's say if it's greater than, say, value t, then you consider that as an edge, right? So simply, that's how you basically calculate the edges. Now, what I've told you right now is the fundamentals of two very famous edge detectors, Sobel edge detector and Prewitt edge detector. Now, there is a bit of pre-processing steps, like you might want to smooth the image, I mean, blur the image so that you get, so that, and also you might want to remove the noise of the image so that you get better edges detected when you are doing this processing. And these pre-processing steps actually vary between various edge detectors. But the crux of it is basically this: find the derivative in the x direction, find the derivative in the y direction, and then get the magnitude, threshold the magnitude, and then whatever is left will be your edges. So this is a simple this is a simple way to find edges in an image using traditional computer vision. And now if we see where can we actually use this, like, okay, now I got edge detection algorithm with me, where can I use this? Now they can be used in, for example, say, license plate detection, and they can be used in autonomous driving wherein you want to detect the edges of the road so that the car doesn't crash into the roads. But of course, like, these are very traditional methods. These were something that were in 1960s and 70s. Now we have come a long way. For example, if we want to actually detect a license plate, we can do OCR and stuff like that. So, but it's, as I said, it's good to know about these age-old methods. So I'll stop my discussion about traditional computer vision here. And if I would actually suggest, if anyone is interested in looking this up or to learn a bit more about various other methods, there are SIFT, there is interest point detection, etc. So I would strongly recommend a lecture series by Professor Mubarak Shah at UCF. So you can find it on YouTube, a very accessible and a very good lecture series that I would suggest for anyone who want to dig a bit more into this traditional computer vision. Yeah. So, I mean, if there are any doubts at this point, any questions, please feel free to ping in the chat and I'll try to answer as soon as I see them. Let's go ahead. And now let's move on. Let's move on to the actual topic of discussion, the reason why many of you might be here. How is machine learning being used in computer vision? Now, machine learning in computer vision as a field has only picked up in the last 10 to 11 years, especially after 2011 and 12, wherein wherein the wherein for the first time a convolutional neural network has bet every other competitor in the ImageNet challenge. So I'm sure like most of you would know what ImageNet is, basically object detection and image recognition challenge. So in 2012, when AlexNet basically reduced the error rate by around, I think it's 10, 11 percentage points. And after that, there was no turning back. Machine learning has been widely used. Convolutional neural networks have been heavily deployed in the field of computer vision after that. Now, just to give a glimpse of how much of interest and how much of research is going on into the field of computer vision, I've just given you a small graph which basically represents the number of submissions. The blue line that you see in the graphs are basically the number of submissions to a very high rated conference called CVPR, which is a conference in the field of computer vision. And the green, so the blue line represents the number of submissions and the green line represents the number of accepted papers. Now, as you see, it has tremendously increased in the last few years. 2019 was really high. In fact, the CVPR 2021, which happened this year, had around 6,500 submissions, if I'm not wrong. And if I had to plot it, I would have to increase the scale of the y-axis here. So that's how much of research that's going on into computer vision right now using mostly machine learning and other techniques as well. So let's discuss a bit about what is exactly happening in this field right now. Like what are the various research directions that are being explored in the field of computer vision? And as a student or as an ML practitioner, what can you do and what are the fields that you can pick up? What are the applications that you can pick up and probably do a bit more of research and contribute to the community? So as you all might know, there is this field of computer vision which has a lot of applications like object detection, semantic segmentation, instance segmentation, etc. A lot of them. On the other hand, you also have this natural language processing field, which also has a lot of applications: machine translation, question answering, etc., etc. So now these are two very different fields, aren't it? But there is another research field which is at the intersection of these two, which requires research both from computer vision and natural language processing. And there are applications which need such sort of collaboration between CV and NLP. Now, I'll give you a few of those applications. The first one of them may be image captioning. What image captioning does is when you're given an image, for example, you're given an image something like this. The system, the image captioning system, should actually output a caption for this image. An example caption could be a plate filled with food on a table. So that's one caption of the image. So to do that, we need the knowledge of both computer vision and natural language processing, right? So that's one application which requires both the fields. And another application is image retrieval, wherein I give a description of an image that I want. For example, if I say, hey, I want the image of a plate filled with food. Now the system should actually go through all the thousands of images it has in the database, and it should pick out the most relevant image to the query that has been asked. So that is what is called image retrieval. And again, that also requires both computer vision and natural language processing. Now, the other application which requires both these fields and which we'll discuss a bit more in detail, in fact, which I find really interesting, is visual question answering. Now, what happens in visual question answering is you're basically given an image, for example, the image that you see on the left, and you're also given a question based on that image. For example, what's the plate sitting atop? Now, the system should answer this question by looking at this image. Now, the system should say, yes, the answer is stable, right? So this sounds interesting, right? But to answer this question, the system should first understand the image it should understand what is present in the image, so which requires computer vision. And secondly, it needs to understand what the question is asking about. Now it needs to understand what does this mean, what's the plate sitting atop means. So it requires natural language processing. And once it understands the question, the system should also be able to reason on the image based on the question. For example, if you ask what's the plate sitting atop, it doesn't need to know that there's a glass jar here, there is a fork here, there are some other balls here. It just needs to understand that there is a plate here and there's a table here. So it needs to reason on the image based on the question that's asked, which makes this visual question answering task, in fact, a pretty tough task to deal with. Now on the right side, I have given another image as well. Like it given an image, it's asking what vehicle is that flag behind off, and then it needs to say it's a van. So now this is the application that we'll discuss in a bit more detail. Now, given this problem statement, a very basic architecture might look something like this, isn't it? You're given an image, and then you're given a question, right? So you can pass this image through a convolutional neural network, for example, a VGG, and then you can get once you pass it through a VGG network, you will again pass it through a fully connected network, and you get, say, 1024 dimensional vector. Now this is how you process the image. Now how do we process the question? You can just use an RNN. Let's say we use an LSTM, and you pass this question through the LSTM, and then you get a fully and then you again pass it through a fully connected network, and say you get 1024 dimensional vectors. Now we do a pointwise multiplication of both these vectors, and we get another 1024 dimensional vector. Now pass it through a fully connected layer, and finally use a softmax function. I assume most of you would know what softmax means, or what CNNs actually mean, and what RNN is. So you pass it through you apply softmax on top of it, and let's say you have 1,000 possible classes, 1,000 possible answers. You pick the best answer, which is, say, how many horses are there in this image. You pick it's 2. Now this is how a very basic architecture for VQA looks like. But here we see, like, I mean, this is very basic. This is the first thing that anyone would come up once you look at this problem statement. But as you see, there are a lot of places in which you can improve this architecture. Now you can improve it on the question part. You can improve it on the image part. You can improve it on the fusion part. So there are a lot of places where you can improve this. But for now, let's just look at how we can improve this image feature extraction part, because this is mostly a computer vision related talk. So let's just see how this can be done. But before we get to that, but before we see how that can be done, I would like to introduce two concepts before we can actually see how we'll improve this part. All right. So the first thing is, I'll define what a scene graph is. Now, what is a scene graph? A scene graph is something wherein if you're given an image, you need to convert that image into a graph, right? Now, where this graph can be used, now this graph can actually be used in many of the downstream CV and NLP tasks, like image captioning and even visual question answering, as we are going to see in some time. And this in itself, like generating this graph from this image in itself, is a big area of research. So let me define what the scene graph is. So this scene graph basically consists of all the objects in the image. For example, you see a man here. So the nodes of the graph are basically the objects that are present in the image. And you see a horse here. So horse would be another node in the graph. You see a bucket here. It's an object in an image, which becomes a node in the graph, right? Now, how do we connect the edges between all these objects? Now, to connect the edges between the objects, we need to figure out the relationship between each of these objects. For example, what's the relationship between a man and a horse? The relationship is feeding. So that's how the edges are formed. What's the relationship between horse and a bucket? It's eating from the bucket. So that's how the relationships, the edges are formed in the graph. I hope the definition of the scene graph is clear, right? Now, I'll again give a very basic architecture of how you might generate a scene graph, like the first very baseline architecture. So what you can do is you can use an object detector, and then you can get all the objects that are present in the image. Now you can get a man, a horse, a bucket, classes, etc. So these all can be done by a simple object detector. Now, after this is done, you want to get the relationship between them, which is probably the tougher part, right? To get the relationships between the objects, what you can do is, for example, if I want to get the relationship between a man and a horse, I can take the minimum rectangular box which contains both these objects. So for this example, it would be a box it would be a rectangle which contains both this orange box and a green box, something that looks like this, just containing those both. Now, once we get that, we can extract the features from this using a CNN, let's say VGG, ResNet, etc. And then we can pass that through a fully connected layer, and then finally use a softmax to, and then pick from, say, one of the possible 100 different relationships that might actually fit in here. So this is again a very basic architecture that you can use to get a scene graph. But there are very highly sophisticated methods. Like one of them can be read here: scene graph generation by iterative message passing. And there is Kern, which has come up recently, I think in 2019. So this in itself is a very big area of research. But let's assume that you use one of those algorithms and then you generate from this image a scene graph. Now, how can we use this scene graph? Because this scene graph that you're seeing right now over here is basically in English, right? But you need to convert it to some mathematical or numerical format so that our computer systems can understand what the scene graph is. So you can do that in a following fashion. Like, you can basically take all the objects, and for all the objects, you can take the corresponding bounding boxes and send those bounding boxes through a CNN, and then you can get those feature vectors for all the objects that are present. And and there are a couple of options that you can use to represent the relationships between the objects. For example, if you want to represent feeding, you can again take the minimum bounding box containing both the objects. You can take the bounding box containing man and horse, like as I said, take the minimum bounding box containing both these objects. And you can use those features after sending it through a CNN, obviously, as the feature vectors of the edges. Or you can use glove, some word vector representations, to represent what feeding is, or wearing is, or eat from is, when you by passing it through by using glove word vectors. So you can represent it in both the ways, whatever way you want to. So finally, you would get a mathematical formulation of this particular scene graph. Now that we have this mathematical formulation, now that we are able to represent scene graph, what we should see is, can we do some processing on the scene graph, or can we do some processing on any graph in general? Can we use some neural networks on graphs so that we can get some meaningful representations out of it? Now, why would we want to do that for, say, for example, for our VQA task? Why would we want to update? Why would we want to enhance the presentations of all these things? And why don't we just keep it the way we have? Like, we have already extracted what the feature vector for man looks like, right? We already know what feature vector for horse looks like. But why do we want to improve it? Why do we want to enhance it? And the answer lies in the fact that now the feature vectors that you're getting, the feature vector, say, for man, is the same irrespective of what object is present by the side of the man. If I replace this horse in the image with a cat, the representations of the man would still be the same. If I replace the bucket with something else, with, say, a toothbrush or a toothpaste, the representation of the man would still be the same. And in almost all of the applications that require computer vision and natural language processing, the the most important thing that you require is the relationships between the objects and not the objects in itself. For example, let's go back. Now, what is the question here? The question is, what's the plate sitting atop? So it's basically asking the relationship between a plate and some other object that it is present on. So it's a relationship. Now here again, the second image, we see what vehicle is that flag behind of. So it's basically asking the relationship between a flag and some other vehicle that's present in front of the flag. So in most of the cases, as you are seeing, you always need some relationships between the objects to be considered while we are doing some processing, right? So now we want to update the relationship of this man and the bucket and the horse, like all the objects present in the image, by looking at its surrounding objects, right? So for that, that's the reason why would we want to use some neural networks on top of graphs to extract those meaningful representations. So let's see. Now on the left, what you see here is basically a simple convolutional neural network wherein you're given an image and then you use, say, for example, a 3x3 filter to extract some useful information from this image. Now, if you think about it, can I use the same convolutional filter? Can I use the same 3 into 3 filter for a graph? Let's see if we can do that. The problem comes from the fact that if you see an image, it has a very particularly predefined structure wherein you say every pixel, like let's assume that these are the pixels that you're seeing here. We say that every pixel is connected to 8 other pixels if it is in the middle of the image, if it's not on the edges. And if it is on the edge, if it is on a corner, then it's connected to 3 other pixels. And if it is on edge, it's probably connected to, I don't know, 5 other pixels. So an image has a very predefined structure. Now that structure is completely missing when you look at, say, a graph. Now this node in the graph is connected to just 2 neighboring nodes, while this red color one is connected to around 5 or 6 different nodes. So we cannot directly use a simple convolutional filter on graphs to extract meaningful representations. So, and that's the reason why we have to introduce a new set of neural networks called graph neural networks. And these have been, these haven't been around for quite a long time, but they are very powerful. They are very powerful neural networks which can be used on almost any sorts of graph. For example, graphs, you can find them in social networking, or even for recommender systems. They use a lot of graphs. So we are trying to come up with a set of neural networks that can actually work on the graph data and not on predefined data like, say, images. So I'll introduce one. I'll just talk about one such graph neural network and see how we can use that particular graph neural network for the original task of visual question answering. Now we call this an enhanced graph attention network. Now the image that you see here is basically the one that we have seen before. I'll just use it to explain this enhanced graph attention network in a bit more detail. So now, as I said, what we want to do here is we want to basically improve the representations of all the objects present in the image, right? We want to improve the representation of man, horse, bucket, glasses, etc. So in order to do that, let's assume, let's for now, let's think that we want to improve the representation of the object man, of the node man in the graph. What we want to do is we want to consider all the neighboring nodes of man and see how important is each of the neighbors to the man. Now, we want to see how important is horse to the man. We want to see how important is a bucket to the man and how important is glasses to the man. Now, in order to do that, we use an attention mechanism. As you see here, we use an attention mechanism A. And to that attention mechanism, we pass three inputs. The first of them is the representation of the node itself, which we represent hi. So we pass the representation of the man. And let's assume we are calculating importance for horse in the first place. So the second input, hj, would be the representation of the horse. And third one, which is rij, is basically the feature representation of the relationship between man and the horse, which is feeding. Now, before we basically pass the representation of man and the horse, we multiply them with a weighted vector. Like we basically pass it to a feed-forward network, multiply with a matrix W basically. And now we pass that to an attention mechanism, and then we get a score which basically says, yeah, like horse has X amount of importance to the man. Now we do this sort of importance calculation for all the neighboring nodes of the man, to the bucket, to the glasses, and anything else that's missing here. So we do this sort of importance calculation to all the neighboring nodes. And once we do that, we apply a softmax on all the importance values so that that all of them basically sum up to 1. So for example, if we say, okay, horse is 0.9, like 90% important to the man, and bucket is 10% important to the man, and all others are not at all important to the man, then we would say, then we would take a weighted average and then update then we basically take a weighted average and then update the representation of the man. something like this, right? So we would say zero point 0.9 into the zero point 0.9 into the representation of the horse plus 0.1 multiplied by the representation of the bucket. So that's how we basically update the representations of man based on all its neighboring nodes to get a final updated representation. Now, one more thing that is worth mentioning here is if you've observed till now the representation of the man is only being influenced by the horse, bucket, and the glasses. Now, if I use this formula, which basically I said 0.9 into the representation of the horse plus 0.1 into the representation of the bucket, we are actually losing the original representation of the man. Like the man is nowhere in the question, right? So in order to achieve that, we simply put a self loop here. We put a self loop so that we also consider man as we also consider the node as its own neighbor, and then use that as well to calculate the updated representations. All right. So now after all this, after using these graph networks, we have got an updated representation of all the objects present in the image. Now, if we go back here, if I replace this particular image representation, if I replace this particular extraction by the graph neural networks that we have just talked about, which basically means you take an image, you pass that through a scene graph generation algorithm, so you get a scene graph. On that scene graph, you apply what you call a graph neural network. Now, using the graph neural network, you basically end up getting a lot of you basically end up getting improved or updated representations of all the objects in the image. Now, there are a lot of ways in which you can go from here, but one of the simplest ways, which let's stick to the simplest way, is you can basically take an average of all the object representations of the image and then pass it through a fully connected layer, and then you can go ahead with the rest of the pipeline as it is. So this is a small improvement that can be done in this baseline architecture to improve the efficiency of this model, right? So as I said, like this is something that's a lot of research has been going on in VQA, and I've given a sort of simple model that would work and a small improvement on top of it, which is helpful. But if you're interested, I would encourage you to read the papers which talk about VQA in much more detail. So I think at this point I would pause for a while, and then I would wait if anyone has any other questions before we move on to the next one. All right, so let's move on. So the next topic that I would want to discuss is few shot learning. So I'll introduce you to the term of few shot learning first, and then I would talk about a very recent. I mean, it was a recent algorithm which. Sorry. So a recent algorithm which and an algorithm which was introduced recently in 2020, which deals with few shot learning. Right? Was someone saying something? I heard. Okay. All right. Not a problem. So yeah. So what exactly is few shot learning, and why do we need it? Now, if you see all the traditional machine learning, all the machine learning models for which are used in computer vision for say object detection or image classification, etc. If you want to train those models, let's say for example you're using a VGG or a ResNet to develop an image classification model. If you want to classify animals, let's say you want to classify animals, for all those for each of the instances of the animals in the given data set, you need hundreds of images, right? Like what I mean to say is if you want to create a dog versus cat classifier, you need to give some hundreds of images of dog, and you need to give hundreds of images of cat, and you need to train the model. And then if you give a new image of a dog or a cat, the model would be able to say, yes, this is a dog, or no, this is a cat, something like that. But getting these hundreds of samples or thousands of samples to train a machine learning model is not always feasible. And at least for dogs and cats, it's fine. You can get many images, all right. But if you go into niche fields, say for example, medical imaging, then if you want to classify whether a given image, whether a given tumor is malignant or benign, or some other medical application, first of all, you to annotate the data, you need a lot of images, which might not be very feasible to get. And secondly, even if you have a lot of images, in order to annotate these particular images, you need to have experienced radiologists, and they are not very easy to find. So we need to somehow do away with this requirement of having large number of images. And another example would be, for example, in the field of agriculture, if you want to, if say, for example, you're given an image of a diseased leaf, and you're asked to predict what disease does this leaf have, or what disease does this crop have, you cannot easily get these annotations because it requires some domain experts to label them, saying, yeah, this is this disease, this is some other disease, etc. So in order to overcome all this, we need to have a sort of a methodology wherein you can classify the images by just looking at a few samples. And if you look at it, that's exactly what humans do as well. Like if you have to train, if for example, if a kid wants to know what a horse is, how a horse looks like, the kid doesn't have to look at thousands of images of horses. You can just show the kid 2 or 3 images. Sorry, you can just show the kids 2 or 3 images, and then you can just show another image, and then the kid would say, yeah, this is a horse. So that's where we are trying to move to. That's where we are trying to go towards. Now, to formally define what I've just said till now, look at the right side, which is called meta testing. We'll come to this term meta testing later, but let's look at what few shot learning does. Now, in a few shot learning, we are given a query sample. For example, we are given this dog breed, and what we are trying to do is we are trying to classify the dog breeds, whether it's Labrador, Pug, etc. Right? So we are given this image, and then we are asked what is the breed of this dog. But yeah, but the system cannot just say that this is this breed or that breed by not looking at anything, right? So we also provide the machine learning model with a few images of other classes, few images of dog breeds. Like here, we are giving 3 classes of dogs. We are saying, I don't know, Labrador, Pug, etc. Like let's say dog class A, B, and C. And for each of the classes, we give some k number of images. Like, and the k is very small. It can be 1, 3, or 5. So what we are saying is, we'll give you 3 different classes, and for each class, we'll give you k number of images, which can be either 1 or 3 or 5. So this particular setting is called n-way k-shot because there are n number of classes, which is 3, and k-shot because each class has, say, 3 or 5 different images to represent that class. So this is called n-way k-shot learning, and they're very small usually, n and k are very small. Now, what the machine learning model should do is, by taking this query, one example from this query set, and it should say to which of these three classes does this particular query example belong to, right? And that's how, and that's what we do for the other examples as well. We take this dog and say, yeah, which of these 3 classes does this belong to, or this belongs to, etc. Now, without any training, like a machine learning model would obviously not be able to do such a difficult task. So now we want to train a model which can do this. So in order to do that, we create another set which we call a meta training set, and this training set contains hundreds of examples of many different classes, but none of the classes in that meta training set will overlap with the classes that we see during testing. I mean, none of these 3 classes will be there in the meta training set. All right. So once we have that very big meta training set, what we do is we try to simulate the test time scenario. We try to simulate what we'll do in the test time. Basically, we pick 3 different classes as we picked here, and we pick k different images from each class, just as we do here. All right. And we take a few query examples, or the examples for which or for the examples for which we want to predict the classes, right? Now, one more probably a nomenclature is that this set from which we compare our given example, our query example against, is called a support set. So this is a support set, and this is a query set. All right. So we create the same support sets and a query set in the meta training phase from a big meta training data set. And again, none of the classes in meta training overlap with any of the classes that we see during test time. So now once we pick up a support set and a query set, we call one such one such support plus query set pair an episode. All right. So now in each episode, we come up with a machine learning model. Let's see, like I'll show you a machine learning model after this, something that can achieve this task. So what we do is we take one image from the query set and we pass it to the machine learning model. And the machine learning model would say, yeah, this image belongs to this class or this class or this class. And then we would say, oh no, this is right or this is wrong. And then we use normal cross entropy loss. And then we back propagate the errors and update our machine learning models. So that's what our machine learning models would learn. Like it would learn to classify between different images, even with very, very less number of samples. All right. Now, what exactly is this learning? It's not exactly learning how to differentiate, say, Labrador or pug that we might see during the test time. It's actually trying to figure out how to differentiate between dog species or how to differentiate between two different images, two different classes, right? So you can do so. So that's what you're trying to learn. You're basically trying to learn how to differentiate between various classes. As such, this will be transferable to classes that you have never seen before. Now, this is called one episode, right? Now you can generate multiple such episodes from this meta training data set, isn't it? And you call that as one epoch. Now you can say, let's say I'll generate 1,000 episodes from a given meta training data set. And I'll call that one epoch. All right. So you can do this training for n number of epochs, just as you would do in any machine learning model. Now, that's how you generate this meta training data set and you train the model, isn't it? Now in the next slide, we'll basically discuss a sample architecture of how this model can look like, how a model which can do a few shot learning can look like. Let's see on the left side of the image. Here we take three classes, just as we have before. Here, as we took three classes, we take three classes. This forms our support set, the three classes on the left, and we have one query example, as we see here on the right. But in the support set, we only take one instance of each class. Here we have taken k shots. Here we have taken k different images, right? So here we just take one image of each class. And now what we are trying to do is, given this test image or this query image, we are trying to estimate, we are trying to guess to which of these three classes is this test image closest to, right? In order to do that, a very simple architecture would be to use a CNN and to generate the embeddings of each of these images, right? And once you generate the embeddings of each of these images, you can calculate the similarity of this particular query example of this particular image with all the three images and see to which of these three images is this representation closest to. Now, how do you calculate the similarity? You can do anything. You can do a cosine similarity or any other similarity measures that you might want to do. So you can use a similarity and then you can get a classification score saying, yeah, like this is closest to one of these three images. That's how you can create a model which can do this few shot learning, right? But if you see here, this particular model has a sort of drawback, or this is very simple. Why? For example, if I replace this particular cat with an image of a man, right? It doesn't affect the embedding of the tiger that we get from here, right? The image, the representation of the tiger would still be the same. That's undesirable because the set of discriminative features that you require to differentiate between a tiger and a cat are different when you have to differentiate between a tiger and, say, a human. Because if you have to differentiate between a tiger and a cat, you might want to look at a different features. For example, you might want to look at how the fur of the animals look like, or you can differentiate how the nose or how the how the whiskers or the eyes looks like, to differentiate between a tiger and a cat. But if you want to differentiate between a tiger and a human being, you want to look at completely different set of images, completely different set of features. You might want to look at the number of legs that the animal has or each image has, so that you can easily classify between a tiger and a man. Or you might want to see how the ears look like, or the downside, or they're on the top of the head, so that you can easily differentiate between a tiger and a man. So this sort of discriminative features are different when you change the other set of images in these, are different for different set of classification tasks. So now in order to achieve that, so somehow we want to consider that particular thing when we want to develop the machine learning model. So what we do is we basically use a set to set function in which you give the inputs as the embeddings of of all the different support set examples. So you basically give the embeddings of the three X classes that you find here. And what the set to set function does, what the set to set function does is basically update the representations of each of these classes by considering the representations of all the other classes of all the other inputs. So now what it does is updates the representation of the tiger based on the representations of the second animal and this cat as well. So this representation that you see as the output of the set to set function are completely are updated representations of the inputs by also considering the representations of its neighbors, of the other elements in the set, right? Now this set to set function can be implemented using a transformer. uh, I'm I'm pretty sure most of you might know what a transformer is. So if not, I would strongly suggest to look up. It's a very highly cited paper. So what transformer does is basically this: it takes n number of inputs and updates the representations of each of them, of the n inputs, by considering all the other inputs as well, using an attention mechanism. It's a bit hand wavy that I've just said now, but I would suggest to go back and read about it if you already do not know about it. So all right, so once you get the outputs from the set to set function, it's similar to before. You just get the output of this query vector and compare it with all these three vectors and see which of them is the closest to match to this particular query sample, right? So this is an architecture that was introduced in 2020, and this was the state of the art when it was introduced. But there have been a couple of more new architectures that have come up in the recent times. But this is a really good architecture, simple to know, uh, to get you started in this field as well. So that's about first few short learning. In case anyone has any doubts, please let me know about this. Uh, And finally, so right, we have learned a lot. We have seen the machines are able to do really amazing stuff. They are able to see visual question answering. They are able to do few short learning by looking at just a few images. So does that mean we have already done a lot? Like, does that mean machine learning is almost a sorted problem? It's pretty well. Well, the answer is no, because take a look at this cartoon. What does this say? A person A comes and then he says, "Hey, is this your machine learning system?" The second guy says, "Yep, you power the data into this big pile of linear algebra and then you collect the answers on the other side." The first person says, "What if the answers are wrong?" The second person says, "Just stir the pile until they start looking right." So in a way, that's one of the problems that we have with the current machine learning models. Explainability is something that's pretty much missing in most of the models. I mean, in a way, there is a lot of research going on, and in fact, attention mechanisms are one sort of research direction which they say, like, attention mechanisms can explain why the machine learning models are giving the outputs that they are giving. But more or less, it's still a hot topic of discussion, wherein people are trying to come up with models which are more explainable to see why they have arrived at some answers. A classic example is, I'm not sure if you've heard about batch normalization, wherein for the first time a concept called batch normalization was introduced. It was working pretty decently well. It is improving the accuracy of most of the neural networks that it was being used in. And then the original author said that it is coming up because it reduces the internal covariate shift in the neural networks, and that's the reason they said that it might be coming up. but further research actually has shown that that's not the main thing that it's coming up. It's coming. I mean, batch norm is basically improving the accuracies because it smoothens or it makes the contours of the contours of the loss a bit more better. So it's basically changing the surface of the loss landscape, and that's the main reason why batch norm is working. That's what one of the later papers actually suggests. So in itself, machine learning is still not completely explained as to why it is working, and there is still a lot of research going on in order to generate explainable models. So there is still a lot more to go, a long way to go for machine learning as such. So, and that's not a topic for today. Let's leave it to some other day. So yeah, so that's all that I have for today. If there are any questions, I'm happy to take them right now.
Yes, sir. There are 2 to 3 questions for you. The first question is a general question. Uh, Let me ask you that. Recently, a video recommendation model was subject to a racial bias and made some insensitive decisions. How does one ensure that such biases do not creep into the system?
Okay, so I think that's one of the main reasons that might be happening is because of the input data that you are giving. If the input data is biased itself, it ends up giving some decisions which are biased as outputs as expected because that's the data you have given. So looking at the data and correcting the data, I think is one of the foremost foremost priorities that you have to take care. And second thing, as I was saying, the explainability of the models that I've just talked right now. So if you're able to explain the decisions of the machine learning models, it would be really great because it says then you can easily figure out, right, that this decision has been arrived not because of some genuine factor, but because of any discrimination of race, sex, gender, etc. So having these explainable models would go a long way in ensuring AI fairness. I hope that answers the question.
Yes, sir, it does. The second question is like, how exactly are two nodes of a neural network graph related? Like, what is the computer vision equivalent of an adjacency matrix?
Oh, sorry. Can you repeat the? Oh, just a second.
Yeah,
Let me just
sure.
go back. Can you repeat the question?
How exactly are two nodes of the neural network graph related? Like, what is the computer vision equivalent of an adjacency matrix?
Okay, that's a okay. Sorry, I might not be very clear when I explained this. So a computer vision equivalent. So I think there are two questions. The first thing is how do you represent the nodes of the graph, etc. If I get it right. And the second question
Yeah,
was basically
the first question is how are two nodes of a neural network graph related?
okay. How what? So you cannot say a neural network graph related. So you can say that the two nodes of graph are related.
Oh,
So neural network graph doesn't have any nodes. It's the graph that has the nodes. So to be clear, so these two nodes that you see here, how are they related? Is by the relationship that they have in between them. Now, when I get all the objects from this image, for example, a man and a horse, now I put them as nodes. And how are these two related? These two are related by looking at the image. Now, these two are related because the man is feeding the horse. Now, this is the relationship that occurs between them. Now, what is the relationship between a man and the glasses? They are related by the relationship wearing. This also gets into the second part of the question, which is what is the computer vision equivalent? So the computer vision equivalent is exactly the same thing that you're seeing right here. If I remove this right hand side, if I remove this graph completely from this, I'm just given an image. Now I want to say that no, I don't want to look at the image right now. Now just give me a more better or a better representation of this image in the form of a graph, because I know I can do a lot of things with graph and not with images. So I say convert this image into the scene graph so that you have a relationship between sort of computer vision, as you're saying, as an image, which is basically a field of computer vision, and a graph, which is, well, not exactly related to computer vision. I hope that answers the question, or if there is anything specific, I can delve into it.
yeah, sure, sir. If there is a follow-up, I may state. But the next question is, If the final prediction of for the FSL depends only on the similarity of the embeddings, how do we make an actual prediction for an unlabeled image after the model has been trained?
Oh, okay. That's a really good question. So, yeah. So, okay. So what the question is basically asking is, if I give a completely unrelated dog, if I'm given a completely unrelated dog image, for example, if I give, say, a breed of a dog which I haven't seen at all in meta training phase, how do you say that, okay, this is Labrador? No, you cannot say that. You cannot, given a random image, you cannot say that this is a Labrador, because until you have shown something, let's assume there is a small kid. Until you have shown to the small kid that this dog is Labrador, that kid cannot say that, cannot just take any random image and say, yes, this is a Labrador, right? So in order to do that, what you always have to do is, you need to give an image. For example, you give this image, and you always have to give some support images. Like, you need to give, say, three different images, and out of which one of them is basically the image that you're asking. And only then the system will say this is closest to this particular image. In future learning, all we do is just say this particular query image is closest to one of these support images. It is not going to say that this is a Labrador, because it doesn't know what a Labrador is. It can just say that this is closest to this image in the data set, and as a human we have to say, yes, this is a Labrador, so it's a Labrador. I hope that answers the question. Yeah.
Yes, sir. Another question. Can you tell us about your research with respect to the health industry? What is it?
Sure. I uh, I'm not sure if I can exactly share the details, because we're still working on quite a lot of projects. Uh, but yeah, so I'll probably leave it at there. So I'm not sure what details I can share. Sorry for that.
Oh, no problem. Another question. So, at what point in your life did you decide to pursue a career in ML, and how far have you had you dived into ML at that point? It's a general question.
Okay, got it. I think, yeah, that's a very interesting question. So, uh, my first introduction to ML only happened when I was in, I think, third year, when I was taking this course on machine learning. And then we had an amazing professor called Aruna Tiwari ma'am, and under her there was a PhD student, Om Prakash sir. So it just happened by chance that we started working on a project on signature verification, and that's how I got started in machine learning and artificial intelligence in general. And it was a good project, so we were really excited by the outcomes of the project, and that's how we basically started reading about it. Uh, I basically started reading about it, and that was in third year and fourth year, right? So after that, I was doing some self-learning on machine learning, but it wasn't as much as I wanted to do. So for the next 2 years, I was working full time as a software developer, but I always wanted to work more towards machine learning, and that's when I decided that I would want to go for an MS and pursue this in much more depth, and then I applied to Oxford. Then,
Thank you, sir. It was really inspiring. Well, we have a follow-up to that FSL question.
uh-huh.
The follow-up is that so while making a prediction in real time, how do we choose the support set of images?
Oh, okay. So when you're predicting in real time, uh, you can one of the examples in the support sets is always the one that you have, and you can select the other support sets as anything that you want to do. Like, you can just say, you can select any random two different dog species as your other two examples. In fact, I've just taken three here. You can make them 100 or 200. Now, why are we actually using few shot learning? I think, to be a bit more precise, is is basically, if you're given for example, let's say a plant has got some particular crop disease. A plant, it has got a disease, right? Now we only and it can be disease A, disease B, disease C, disease D, etc. Now our problem is, we cannot take thousands of samples for each of these diseases and train our machine learning model, right? So what we basically do is, we just say, okay, we'll take 10 different samples from each of these. Like we can only annotate 10 samples for these 4 or 5 different diseases. And whenever a new disease comes, whenever we get a new plant disease, and if we want to classify as to particular which particular disease that this corresponds to, we'll simply use this 50 annotated samples and get it. So, and that's basically the final use case of this few shot learning. You are able to classify, you are able to classify what disease that this plant has by just annotating 50 samples or 20 samples, and not thousands of samples which you had to do before. So to answer your question as to what would you give as the other, like if one of them is definitely the same class to which this belongs to, you would have to give a few more samples. Like for example, in the crop disease, if you assume my crop my crop can have n number of diseases, so you would give all the n number of samples. For example, if a cotton plant can only get diseases which are related to cotton, right? It might not get diseases which are related to some other plant. So you would give all the diseases that are related to cotton plant, and then you would give the leaf that you have under that is under question, and compare it with all these different diseases. Does that answer your question?
Yes, sir. So we're done with the questions. I would like to, at last, I would like to ask you an advice. Like for an undergrad as I am, what should we do? We are, for example, I'm in second year. What is the course of uh, learning that we should follow to pursue a career in ML, in any domain in ML?
Sure. So yeah, I think that's a very relevant question nowadays because yeah, I mean ML is almost everywhere, and I assume in the next few years, ML is going to be like how the software development is right now. So it's always good to be at the forefront of it. And to answer your question on how should I get used to it, or I mean on how should I learn about machine learning, I would say first get started because you're just very young, right? You're just in the second year, so you should probably have an understanding of linear algebra, and optimization. I think those are already taught in undergrad, from what I remember. So once you have these basic concepts in place, what you can do is learn a few courses on Coursera or EDX. The course by Professor Andrew Winja, I think, is really amazing. So first you can do the Coursera course, and then I think you should definitely do the one uh, that is that is taught by him at Stanford. That was also a really good course. The one that you see on Coursera, I think, is a very watered down course. It's basically much simplified version of the original course. So once you do this basic course and you have all your fundamentals about linear algebra and all everything set right, you can do that Stanford course. That would be one of the first steps that you can do. And once that is done, if you want to get into specifics of, say, computer vision or natural language processing, you can take the courses CS 231N or 229 if I'm right with the course numbers. So they are offered by Stanford, again available on YouTube free of cost, which is really good. And if you want to get into more into computer vision, traditional computer vision, which I think everyone should have an idea about, you should I would suggest the course by Professor Mubarak Shah, which is also very good. And there is another course. I think once you're clear about this machine learning concepts, etc., there is another course on deep learning. I think it is called deep learning. I'm not exactly sure if I got the name right or if the course name is something else, provided uh, by Oxford University on YouTube. So you can probably search deep learning Oxford, and then that's a very good course as well. It has a few lectures, I think 10 to 15, and that's really amazing. So once you get all these things right, I think it would take quite some time. It would probably take the time until fourth year until you graduate. After that, if you still want to, I mean after that, I mean of course you would want to, after that, when you want to get into when you want to get into actual machine learning fields, one very important thing is probably research. uh, it for software development, the research and this for software development, the research is entirely different from, say, what you do in practical, like in companies. But for machine learning, if you want to do something in companies, or if you want to attend for any interviews or get hired, I think research is probably the only way to go ahead. So you can pick up one of the problems that, for example, we have discussed here, and then you can delve deep into that field. Usually I also try and I also try to work on some projects in my part time. So if anybody is interested, you may contact me. I'm not sure. I wouldn't guarantee that I would work on it, or I would definitely work on any project in the near future. But if anyone's interested, I'm usually working on some side projects sometimes, so I can I can help you out.
Yes, it was really grateful of you. Now I think we have reached the conclusion of the event. Uh, I would like to present the vote of thanks for today's webinar. I would like to thank our guest lecturer, Mr. Vidyuranya Sai, for taking out his time from his busy schedule and inculcating our cognitive minds with his knowledge and expertise. Today's lecture and webinar was full of knowledge and curiosity. We all got a lot of incentive to learn computer vision and to explore other domains of machine learning and artificial intelligence. I would like to thank the Student Affairs IIT Indore for giving us this opportunity to organize this event. I would also like to thank the volunteers who worked really hard to make this event successful. Most importantly, I would like to thank you all for being here. Thank you all the participants for paying attention, and thank you all for your curiosity. Please stay tuned for the future events by IIT Indore and the Synaptics Club. Thank you, sir. Thank you all the participants. Have a nice day. Thank you.
Thank you everyone.